Hello everyone, and welcome back to this series on multivariable calculus. In this video we're going to begin our formal discussion of some of the principles that we need for multi-calc. As you already know, we will be dealing with 3 dimensions and also higher dimensional surfaces. And in the realm of calculus, especially from single variable, you should remember that both derivatives and integrals can be formulated and are often formulated from the idea of limits. So in order to build calculus, such as derivatives and integration techniques in the multivariable realm, we need to have some idea on how to deal with limits in the multivariable realm as well, which is what we're going to sort of be discussing today. So let's first off review some of the principles that you should remember from single variable calculus when it comes to limits. So let's first off assume, for simplicity, that f is a function that maps the set of real numbers to the set of real numbers. So the set of real numbers is the domain. And let's assume that a is a particular point in its domain. Let's also assume that the left-hand limit of a function is equal to L subscript L for left limit. And let's assume that the limit as x approaches a from the right of that function is equal to LR, or the right limit. So we say that if L left and L right are both equal to each other, assuming finite of course, then we will write that the limit as x approaches a of the function is equal to L, where L is the value for which LL and LR are equal to. Right? Now, the reason that it's important to understand this idea is because we have this notion of approaching points from directions. So on the left we have x as x approaches a from the left and as x approaches a from the right. So if we view this from, say, a real line, right? So here's our x-axis, here's our point A. We can approach this point A from the left, so that's A minus, and we can also approach A from the right, so that's A plus. There's no other way to get to this point along this horizontal line. Now, when we do increase this to higher dimensions, we have a really big complex issue to deal with, right? So for 3 dimensions, in particular 2-dimensional inputs, we're interested in statements such as the limit as xy approaches a b of some 2-dimensional input, fxy function. This is equal to, say, L. Like, what does this even mean? And here we're assuming that f takes the cross product of r to r and maps it to r here. And we're going to assume that for simplicity, AB belongs to the domain of f. But if you do remember, a point doesn't need to belong to the domain of a function or even be defined in order for the limit to exist. I'm just having this here just for some base idea. Now, if we have our x-axis and y-axis here, and let's assume that our point here is AB, how can you approach it? Well, you can obviously approach it from the left-hand side, just like we did above. You can also approach it from the right-hand side, like we did above. You can also approach it from the top. You can also approach it from the bottom. You can also approach it from diagonals. You can also approach it, if you're a little bit more creative, via a parabolic path, such as that. And you don't even have to approach it in a nice way. You can approach it in very strange ways. For example, along that path, right? So that would be one path that you could take to get there. So there's not only 2 paths we need to consider. We need to consider infinitely many paths and the curvature that those paths can take. So how can we analyze every single possible path to traverse across, right? So that obviously shows how multivariable calculus can potentially be very, very complex to deal with. So let's start off with a very numerical example to sort of see if there's any theoretical things that we can use from the ground up. So let's assume that we're interested in the limit as xy approaches the point 2, 1. And let's assume that the function that we're dealing with is x squared plus y squared divided by 3xy plus 1. Right? So notice that this is a rational function because we have a polynomial on top and a polynomial on bottom, and rational functions are only undefined as long as the bottom is not equal to 0. So this function, let's assume that this is function f, is discontinuous if and only if 3xy plus 1 is not equal to 0. Or it's discontinuous. Actually, let's say it's continuous. It's continuous if and only if that does not equal to 0, because it's discontinuous if it is equal to 0. Right? So that means if we rearrange for y cannot be equal to negative 1 over 3x. So y cannot be equal to negative 1 over 3x. So if we look at our domain region, so this is going to be r cross r. So this is the path we need to look at. Some people also write this as r2. So when y is equal to negative 1 over 3x, where is that particular range? So that curve is going to be this area here and this area here, not drawn to scale, right? And our point is 2, 1. So 2, 1 is going to be located somewhere there. So that's 2, 1. And these points along these particular trajectories, those are our problem points, or points of discontinuity. So as long as this function is continuous, then we know that the limit will be equal to the function value. Right? So since we can justify, at least in some sense at this moment, that this function is continuous at 2, 1 because it's a rational function. Rational functions are only discontinuous when the bottom is equal to 0. That means this is going to be equal to 2 squared plus 1 squared all over 3 times 2 times 1 plus 1. Right? So that's going to be equal to 2 squared plus 1. That's going to be equal to 5. And 3 times 2 is 6 plus 1 is 7. So 5/7 is the value for which this curve approaches as xy approaches 2, 1 from any path. Right? So this is true for any path taken. That's very important to keep in the back of your mind for now. So using the previous example as sort of a guiding light, if we have a function that maps, for example, Rn to R, so it has n inputs, not just 2, it could be 50 or 500, with n being greater than or equal to 1, of course, with A being a point or a vector in that high dimensional space, then if we can establish that f is continuous at that vector point, then we can say that the limit as x approaches a from any direction, regardless of dimension of that function, should be equal to f evaluated at that point. So let's look at just another example to sort of see if we understand that main idea. So another example, let's call this example 2. Let's assume that f of x, and here x is going to represent a vector, so let's actually bold it a little bit. So f of fancy x will be equal to 3 little x squared y plus y z squared plus 2xy plus xyz. Let's also have 1. Right? So what type of function is this? Well, this is obviously a polynomial in x, y, and z, or we can say in fancy x. So it's a polynomial in vector form. So let's assume that we also want to see what's going on at the point A, which is equal to minus 3, 1, 2. So what is the behavior of this function at this particular point? So therefore, what is the limit as x approaches A, right, of this particular function f of x? Right, so since it's a polynomial in x, y, z, that means it is continuous in x, y, and z, or more generally, in x. So since it's continuous, that means this is going to be equal to f of a. So we can just plug in our values into our function, and that's going to give us our limit. So this is going to be equal to 3 times minus 3 squared times 1 plus 1 times 2 squared plus 2 times minus 3, 1 plus x times y times z plus 1. And what is that going to be equal to? So it's going to be equal to 9 times 3. That's going to be 27 plus 4 minus 6 minus 6. And that's going to be equal to, what is that going to be equal to? Let's assume that's just going to be equal to 20. Right? So that's going to give us our particular value at that particular vector point. Let's not forget our little 1 to make it 20, else it's just 19. Right? So there's that particular function. Quite easy. So if it's a polynomial, nothing is scary. Now let's look at another example where it's not as trivial. Let's consider the limit as xy goes to 0, 0 of x squared minus y squared all over x squared plus y squared. Now, this function obviously is not continuous at the origin, therefore we have a discontinuity. So we have discontinuity at xy equals 0, 0. So we can't just plug it in. Right, so we have to sort of approach it from different points and see if it equals the same exact thing. And if we can find any two paths that produce different limits, then you have proof that the limit doesn't exist as well. So let's see if we can approach this along the x-axis. So we're going to approach 0, 0 from the left and 0, 0 from the right. So if we sort of draw a graph here, we're going to be approaching along these directions, which means that y will be equal to 0. So when y is equal to 0, what do we get? So we're going to have the limit as just x approaches 0 of x squared minus 0 squared all over x squared plus 0 squared. So zeros don't contribute anything, so we're left with the limit as x approaches 0 of x squared over x squared. Obviously a removable discontinuity because that's just the limit as x approaches 0 of 1, which is equal to 1. So is the limit equal to 1, or is this just a path-dependent limit? So let's choose another direction. So along the, let's do y-axis. So if we approach this point along the y-axis, for example from the top and from the bottom, then we have that x must be equal to 0. So that means we're going to have the limit as y goes to 0 because x is 0 here. We're going to have 0 squared minus y squared all over 0 squared plus y squared. Zeros don't contribute anything as usual, but don't forget there's negative signs, so the limit is y approaches 0 of minus y squared over y squared. Y squareds cancel, still a removable discontinuity, so we have the limit as y approaches 0 of minus 1, so we have minus 1. So since the x-axis path limit and the y-axis path limit are not equal to each other, so we found two paths that produce different limits, that means we can say that the limit as xy approaches 0, 0 of the function x squared minus y squared all over x squared plus y squared does not exist. Or some people also say it's path dependent. Some people only care about certain paths, but if you're just looking at the overall limit, then we clearly see it does not exist. So let's consider this example, the function x squared y over x to the fourth plus y squared, and let's assume that 0, 0 is going to be our point of focus, again because it's obviously not in the domain, so whether the limit exists is up for investigation. So one can show, similar to the last example, that if you approach 0, 0 from the vertical direction or the horizontal direction, you'll actually get the same exact number, in particular 0. So what happens if you choose any other line in particular, which also is going to include, your horizontal and your vertical components? So how do we approach along arbitrary curves? So let's approach along the line y is equal to mx, m being the slope. All right, and m can be 0 if it wants to be. Now keep in mind 0, 0 must be on that path, else you can't approach that point on that path. That's a very important thing, right? So 0 is equal to m times 0 as long as m is a finite number, so everything checks out there. So if we approach along this particular line, then the limit as xy approaches 0, 0 of this function, fxy, will be equal to the limit as x, so y is going to turn into mx of f of x mx. So notice that in this particular thing, there's only one variable in particular, x in focus here. Right? So we can just re-represent everything in terms of x only. So this is the limit as, and keep in mind that's going to approach 0, 0. So the limit as x approaches 0 of what? So we're going to have x squared times y, which is mx, all over x to the power of 4 plus y squared. Right? So now we have a one-dimensional limit. We should be able to deal with this in our traditional way. So we have the limit as x approaches 0 of, so we're going to have mx cubed all over x to the 4th plus m squared x squared. So notice that we have an x squared on the top and we have an x squared on the bottom, for which can cancel out. So let's just simplify that. Nice little removable discontinuity potentially. So we're going to have the limit as x approaches 0 of mx over x squared plus m squared. Now, notice that this curve is not discontinuous at 0, 0, because when you plug in 0 into the denominator, you get m squared, right? So as long as m is not equal to 0, you don't really have any scary things, but you could use the L'Hopital's rule and see that that's actually not going to give you much any issues, okay? So when we plug in 0 here, notice that we're going to get just m times 0 over m squared, and as long as m is not equal to 0, this will be equal to 0. And this is going to be true for all m not equal to 0, and it actually is true for both m is equal to 0 and m is equal to positive and negative infinity. So that's actually pretty interesting, so the vertical and horizontal lines as well. So we approach this point along any line and we get the same exact answer. So does that mean that the limit exists? No. Right? So at this point, what we've done here is just approach this point along any line, right? So now what we need to do is try and approach it along some other curve. And instead of a line, the next curve will probably be, say, a parabola. So we want to approach along these particular objects, right? Something like that, right? Or you could do in that way as well. So how can we approach along any parabola? And again, 0, 0 must be along that trajectory. So what we're going to do is we're going to approach along, let's do the path y is equal to ax squared. So nice basic parabolic function. And let's see what happens here. So therefore, the limit as xy approaches 0, 0 of fxy, this is going to turn into the limit as ax squared approaches 0, 0 of f of x ax squared. Notice again that this is still a function of x only, so I can switch this into a limit of x only as well. So that means this is going to be equal to what? So this is going to be the limit as x approaches 0, and then we're going to have x squared times ax squared, and on the bottom we're going to have x to the power of 4 plus ax squared, the quantity squared. And that's going to be equal to the limit as x approaches 0 of, we're going to have ax to the power of 4 all over x to the power of 4 plus a squared x to the power of 4. We have an x to the 4th in every term, so we can actually cancel that out. So we're going to be left with the limit as x approaches 0 of a divided by 1 plus a squared. Right? And what is this? Well, as x approaches 0, there is no x, so we just get a over 1 plus a squared. Right, so the limit of this function is equal to a statement that is a function of a. So if you have different a's, you actually get different limits, right? So different parabolas or different parabolic paths give you different limit values, right? So that means what? So we can conclude that the limit is path dependent, and since it's path dependent, that means the limit as xy approaches 0, 0 of this function does not exist, at least not in a unique manner. Now, you might be thinking to yourself, for that last example, what if the limit does exist along any linear path, it exists along any parabolic path? Would we really go and try every cubic path, every quartic path, every quintic path, and just increase the degree until we possibly find a path for which is dependent in terms of its value, right? Like, how do you really try all possible paths in order to prove that the limit does indeed exist? Now, generally speaking, there does not exist, at least for all functions, a L'Hopital's rule equivalent when you have like a 0 over 0 or an infinity over infinity or another indeterminate form, right? Which is kind of unfortunate, and that shouldn't surprise you due to the complexity of multivariable functions. So instead, what you would have to do in order to consider all possible directions is to somehow map a two-dimensional space to a one-dimensional space. That is it possible to send x and y to a space that only depends on one variable? So for example, if x and y both go to 0, is there another variable that also goes to, a point that you can sort of quantify? So a transformation of coordinates is sometimes a good strategy. So transform coordinates, for example, a 2D coordinate system into a 1D coordinate system or a 1 star D coordinate system. And I'll describe sort of what I mean by that. Because if you look at this particular function, x squared plus y squared, you're like, oh, maybe I can transform to polar coordinates. Right? But you might be thinking, well, polar coordinates has two variables too. It has r and theta in it, and you would be right in that context. So let's actually look at how we would approach this in the polar coordinate realm. So remember, there are three identities that you definitely should know. In particular, x squared plus y squared is equal to r squared. That's the first. And then x is equal to r cosine theta, and y is equal to r sine theta. So those are the three primary identities. You could also write, for example, theta is equal to the arctangent of y over x. That's another one, but I actually don't need that here. Now, one very important thing you should note, that as xy approaches 0, 0, if we solve this particular equation for r, what you're actually going to have is r is equal to the square root of x squared plus y squared. So as xy goes to 0, 0, then we can see that r is going to go to the square root of 0 squared plus 0 squared, which is equal to 0, right? Independent of theta. And that's very, very important. That looks like the empty set. Let's not write theta like that, else theta might get upset, right? So it's independent of theta. So as xy goes to 0, 0, r, a single variable, goes to 0. Right? So maybe we can solve this with one-dimensional calculus, and maybe use L'Hopital's rule if it comes up in that one-dimensional analog. So let's see what actually happens with our particular example, because that's actually very, very useful. So what do we got? So the limit as xy approaches 0, 0 of x squared y all over x squared plus y squared. This is going to be equal to, so as xy goes to 0, r goes to 0. So we're going to have the limit as r goes to 0. And then x is going to be what? X is going to be equal to r cosine theta squared, and then r sine theta, all over x squared plus y squared. That's just going to be equal to r squared. Now notice we have an r, and an r squared, so they're going to cancel out. So we're just going to be left with the limit as r goes to 0 of cosine squared theta times sine theta. And also, that should be an r squared. So technically, we still have an r hanging out there. Right? So if that r didn't cancel, notice that this would depend on theta, which means it is again path dependent. But notice that we do have this r here, so we're actually very, very lucky. So let's sort of factor that out to sort of see what that means. So we're going to have this is equal to cosine squared theta times sine theta. So that's a constant as far as the limit's concerned. We have the limit as r approaches 0 of r. So r is going to be equal to 0. And then we're going to have 0 times something that's going to be equal to 0. So notice the limit of this is equal to 0, and that's going to be for all theta. And usually theta is going to range from 0 to 2 pi. Right? So that means what? So that means this limit does exist and is equal to 0 because all paths are sort of considered in this one-dimensional coordinate transformation, right? So polar coordinates and other transformations such as spherical and cylindrical can also come in handy when you're working with higher dimensional inputs. But those are some of the things that you definitely should keep in mind with working with functions of several variables when it comes to limits, and we'll discuss continuity, differentiability, and integrability in other videos. So I hope you enjoyed this video, and I'll see you in the next one. Take care.